Today, we'll be discussing the moving average within the context of time series analysis, drawing information from the Finance ResearchGate website. However, before we proceed, it's crucial to first delve into the fundamental mathematical principles that underpin this technique. So, the moving average model is quite different from the autoregressive model, or AR, that we thoroughly discussed in our previous session. With the moving average, we specifically allow the impact of errors or unexpected shocks to carry over and propagate into the subsequent period. This then represents the fundamental and typical framework of an MA model.
The variable of interest could be price, the GDP growth rate, or return.
Regardless of the specific variable we happen to be using, it can be expressed as a function of the error of shocks for that particular variable. This includes both the current error of shocks and the one from the preceding period. The previous one naturally will be assigned a somewhat lower weight. For instance, that value could typically be around 0.5. So theta in this context represents the coefficient directly attached to those previous shocks. The concept here is that it might take a while for any given error to fully manifest its impact on xt. Therefore, an error that occurred in the preceding time frame will certainly continue to exert some influence, though its magnitude will be less significant compared to the immediate current error affecting xt. In this particular situation, we're not actually dealing with xt minus 1. Instead, what we are dealing with is the error of shocks that originated from the previous period. So, when we examine this particular model, we find that the expected error is precisely 0. The variance remains constant throughout, and the covariance is also 0. Therefore, what we're dealing with here is essentially a case of pure white noise errors. Because the expected value of the error is 0, the variance of the errors remains constant, and there is no autocorrelation present within the error term. This therefore implies that we are working with ID, meaning identically and independently distributed errors, or, more simply put, white noise errors. So, the impact of our current shock today influences the series right now, and it also partially affects the series in the upcoming period. This means these shocks possess a brief memory. Their effect is quite short-lived. But of course, that effect will eventually die out after several periods, depending on the specific MA model being used. For example, MA1 means that we are only considering the error from one period prior. If we have an MA2 model, we are going to extend that to include the error from 2 periods ago, and other related aspects. So the overall structure of our model will look something like this. Here we have the Q parameter. This Q value is either set by us, or more commonly, the user will determine it based on the specific variable of interest they are analyzing. Therefore, if you were to halt the process at this particular point, for instance, that configuration would represent the MA1 model. If we extend that for 2 periods, that will be the MA2 model, and so on. The variance of the stochastic process xt, considering the premise that this particular process adheres to a moving average autoregressive autocovariance path, is explicitly defined and given by the mathematical equation presented here. Since we are dealing with error shocks, we consider the current error shocks variance added to the previous period's error shocks variance, which is then multiplied by theta squared. This expression will then simplify and translate to the quantity of 1 plus theta squared multiplied by the overall variance of the error term. So the variance of x, logically, is a function of the variance of the underlying error, given that the MA model assumes that the xt variable is affected slowly by the impact of error shocks. The covariance between the variable xt and xt minus 1, specifically, we're discussing the autocovariance, assuming that the xt variable follows an MA process. The entire framework is defined and established by this particular term. Observe that the covariance, for instance, between the error term at time t and the error term at t minus 1 or even t minus 2 is precisely 0. This is because we previously assumed that there is no serial autocorrelation present within the error terms. Consequently, the only remaining term in our equation is this specific one, which is simply the variance of the error multiplied by the parameter theta. So, the autocorrelation coefficient, when we consider the moving average framework, is calculated as the coefficient of theta, which is theta divided by 1 plus theta squared. For example, if the value of theta is quite large, this implies that we will observe a significant level of autocorrelation. So in this specific case, what does this mean for the lengths of the xt? And this, the variable xt minus 1, is determined by the parameter theta, because this xt minus 1 actually consists of 2 distinct components, one of which is the error term from the previous time step, t minus 1, and the significant error that occurred in the preceding time period. So the error components present within the xt variable are directly causing the autocorrelation observed between xt and its preceding value, xt minus 1, a relationship which is then quantified by theta. For example, if we take this numerical case where we've already found the error terms, pause, and if we then assume that our parameter theta is precisely 0.5, pause, we can quite easily determine the xt value according to the moving average model. It's simply the current error term combined with the previous error term, which has been multiplied by 0.5. The previous error term, you see, it did not die out completely. Its effect will continue to remain significant for the next period, and that's precisely why we establish a clear connection between the previous period and the current period. Therefore, by carefully working through this specific example, we can determine the value of xt by following the moving average path. This implies that every single shock will influence the time series for a maximum of just one additional period. This example is something we can definitely utilize in finance. Let's consider a situation where we have a specific price function. To ensure that the variable we are primarily interested in is truly stationary, a common and effective method is to calculate its first difference. So whether we take the direct difference, or perhaps the logarithm, or even the difference in the log levels, this calculation will effectively provide us with the rate of return. Ultimately, this derived value would then represent a clear function of that very rate of return. And there's also what we refer to as a noise or an error term that needs to be considered. So the actual observed return that we ultimately see is essentially a direct function of the underlying efficient return plus the influence of that additional noise component. When a market achieves true efficiency, it fundamentally implies that the actual observed return and investor experiences will be exclusively and precisely equivalent to the true underlying efficient return. Any extraneous or random fluctuations, often termed noise, should not influence or be incorporated into this true and fundamental rate of return. Consequently, to accurately assess whether a market truly exhibits this level of efficiency, we can effectively utilize MA analysis as a robust and reliable testing methodology. This could be applied to the entire market, or alternatively, we might choose to focus on a single stock or perhaps a select few. However, the fundamental concept here is that if an error term were to propagate and carry over into the subsequent period, this would imply that our model doesn't fully capture efficiency because we've permitted some past disturbance, a kind of noise, to influence the future rate of return. If the market is truly efficient, these noises would be filtered out and completely eliminated the very moment they initially occurred. However, if the mistakes made in the preceding time frame didn't vanish right away, and instead we permitted them to persist and be transferred into the subsequent period, this indicates that the market requires a certain amount of time to adequately react to incoming information. This ultimately means we do not possess a state of perfect market efficiency. So we're able to use that particular approach and then thoroughly test the overall market efficiency by employing the MA model. So first, I need to carefully select the appropriate time series data. And then what we'll do is we'll go ahead and select the monthly option. For instance, let's choose the whole period and then apply it. It will take quite a bit of time to construct the functional sample. All right, so for this particular step, we're going to proceed with selecting the appropriate monthly return. And then we will apply this methodology to every single firm in the market. This is how we will construct our comprehensive market index, by calculating the average monthly return observed across all these firms for every single month. We're not going to restrict this to just a single sector or a particular firm. Instead, we'll be leaving these selection boxes completely empty. Therefore, by default, we will be selecting every single firm available. After that, we simply proceed to click the Apply button. Zion, what we've done here is construct the monthly market return. We achieve this by utilizing data from every single firm that's accessible on this particular website. This then forms a comprehensive time series spanning a significant period from 1962 all the way up to the year 2024. You can quickly check for stationarity, which is a crucial concept that we previously discussed in a separate video. For this particular analysis, the augmented Dickey-Fuller test, or ADF, is quite significant. Based on the results of this test, we can confidently conclude that our time series data is indeed stationary. Okay, so to successfully run the MA model, our next step is to access the classical time series model box. Within this section, one of the specific tools available for our use is the MA model. Therefore, we will proceed to select MA from the list of choices. So the MA, or moving average, is calculated using the errors. But how do we actually go about finding these errors? It's simply the actual observed value of the variable of interest minus its expected value. This expected value in turn can be estimated quite effectively by using a constant term and incorporating any past inferred shocks. So, after you've clearly specified this variable, the computational model designed for this application will then estimate the associated error shocks, and following that, we will then proceed to run the MA model. Again, the MA model, or moving average model, is defined by this formula. In this framework, we regress the current observed level of our variable of interest against a weighted sum of the error shocks occurring in the current time period, and also incorporate the influence of all previous error shocks from earlier periods. So, for instance, if we select a moving average regression of order 1, then the parameter Q in our model would specifically be set to 1.
And let's now fit the model.
Alright, so here we are looking at the outpost, which serves as our initial reference point. The constant factor we're observing in this particular scenario is quite significant. Specifically, it registers at approximately 1.9%. This means the average monthly return is nearly 1.5% when we consider the entire sample period. To properly analyze this, you can simply multiply that specific figure by 12%. This calculation will then provide you with a rough estimate somewhere between 20, perhaps even up to 24%.
And now, in the subsequent discussion, we will proceed to thoroughly examine and analyze the specific characteristics of the moving average term.
Here, the moving average term's value is 0.07. The z-value, which is essentially equivalent to the t-value in statistical analysis, appears to be not particularly significant when we consider it at the conventional level. However, this z-value does hold some statistical importance if we carefully consider its relevance relative to a more lenient 10% significance threshold. However, we do not possess a sufficiently strong level of statistical significance, and as a result, we are led to the conclusion that it will be quite challenging to allow these unexpected error shocks to propagate and spread their influence throughout the entire next month, and as a direct consequence, we do not foresee any significant short-term effects, which implies that the prevailing price level and consequently the financial return will accurately reflect all pertinent and significant information available within the current period. It's crucial to understand that nothing from this period will simply propagate to the next month. That is the most important conclusion. Thank you for listening.